Okay, recall that our original equation, when we solved the homogeneous equation, our characteristic solution, if delta was bigger than omega naught, our square root would be real, so that we get two real solutions with exponentials having negative coefficients of t, and we'll establish in a minute that both these coefficients are negative, and one being negative delta plus the square root, the other being negative delta minus the square root. So our characteristic solution then is going to be a linear combination of these two exponential functions. The coefficients of t between these two functions differ. Now recall that delta is bigger than omega, so that this is a real number. And also note that the square root of delta squared minus omega naught squared is less than delta. Just think, the square root of delta squared itself would be equal to delta, and if we subtract, we get a smaller number inside the square root, so it's going to give us a smaller result. So that this is smaller than delta in both cases. Now, this being smaller than delta, when we add it to negative delta, we still have a negative number, so that we do have an exponential decrease in this term. And here, our negative coefficient is greater in magnitude than it is over here because we're subtracting a number from delta, giving us a bigger negative number than the one we get here. Now that has the following effect on the graph of the exponential functions. Should have said the graphs of the exponential functions. The function with the greater negative coefficient of t is going to decline more rapidly, as you should understand from the basic numerical behavior of an exponential function. And the one with the lesser coefficient, lesser negative coefficient of t, in other words, negative coefficient of lesser magnitude, is going to decrease less rapidly. Also, we can note that the greater the value of omega naught, the greater the difference between these two coefficients, because the greater, well, what I started to say just isn't true. A greater omega naught is going to make the square root smaller, which means that you're either adding or subtracting a smaller number from the negative delta, and that's going to imply less difference between the two graphs. I've just changed these labels, the subscripts on the C's down here in case you notice the difference. Okay, now if C2 is negative, that means that the multiplier of the exponential function with the more rapid approach to the axis is going to have a negative exponent, which is going to lead you to a graph that looks something like this. So this would be the graph of C2e to the negative delta minus the square root of delta squared minus omega naught squared quantity times t. And assuming that the magnitude of C2 is bigger than C1, and let's specify that C1 is positive. That might be implicit from the graph, but let's write it down very clearly. That our C1e to the negative delta plus the square root of delta squared minus omega naught squared t would look like this. I probably shouldn't have to point it out, but note that both of these graphs have the same y-intercept. When t is equal to 0, both of these functions are equal to 1. So that our value of C1 would be here, our value of C2 would be here. If I look at the behavior of then the graph of YC, which is the sum of these two functions with these coefficients, with these conditions on the C1 and C2, we see that the sum of these two graphs is going to be the sum of this positive y value here and this negative y value here. So we take this negative y value, brings us down to here. We add this positive y value. At t equals 0, we get this point. Then there's a point at which the graphs have equal and opposite values. That would be maybe about here. So the y value of this graph is positive, the y value of this graph is negative. I might want to come over just a little further to make that happen. So that the value of the function would be 0. The value of the characteristic function would be 0. Then, to the right of this point, this graph is consistently closer to the axis than this graph, so that there'll be some point where the sum function is a maximum, and then it's going to stay below the graph of the positive function because the negative function will always bring it down a little bit. But the negative function is going to be very close to 0, so the graph will actually approach the graph of the positive function, so that the graph of this function could look something like this. So that it's possible for the system to be given an initial velocity, to start with some negative, or to at some point have a negative position, and then to hit the equilibrium position, which corresponds to y equals 0, and overshoot that position, but then to simply approach the equilibrium position from the other side as an asymptote. So what we would have, for example, if this is the equilibrium position and the object is here and it's given a sufficient velocity, it could overshoot equilibrium, but then it's just going to kind of slump back toward the equilibrium and approach it as an asymptote as time approaches infinity. Now this would be the transient behavior of the system. The non-homogeneous part of the solution to the equation doesn't really care what the value of delta is as opposed to the value of omega naught. So that even if the damping is high, the solution to the particular, or rather the particular solution of the equation is still going to be governed by the coefficient f over 2 delta omega naught m, just that delta is a little bigger, so that the amplitude is going to be somewhat smaller. We're still going to get the term f over 2 delta omega naught m sine of omega naught t, so that that oscillatory behavior will be added on to this behavior of the system, so that we might have a transient by this curve, an oscillatory behavior by this curve, and when they're added together we would get a function that might look something like this. And of course there's a very wide variety of the way solutions of this nature could combine. The oscillatory solution might have a greater or lesser amplitude and a greater or lesser period and frequency, so that there's no single graph that could depict all possible behaviors. The initial conditions could also imply positive values of both C1 and C2, in which case your two graphs would be on the same side of the axis, so you would not overshoot the equilibrium position the way this one does. And there are other behaviors. I just wanted to give you kind of a general picture of what will happen if you don't have an oscillatory system. An oscillatory transient. And I repeat that the oscillatory transient happens when delta is bigger than omega naught, the non-oscillatory transient. And there are only really two possible behaviors for non-oscillatory transient. You overshoot the equilibrium position one time and then come back to it, or you simply approach the equilibrium position in a more or less exponential fashion. Superimposing that transient behavior with the long-term behavior, we get the ultimate behavior of the system, both during the transient and the long-term phase.